Well, okay. I guess you are ready. I put in the title of my slide virtual machine programming for everybody, but I try to trick some people in, but I guess it didn't work so much. My name is Javier Pimás. I work with the B team in B project. And well, what I'm trying to show you today is how we would like to work and how we actually work on developing our DMR, our dynamic metacircular runtime, which is our replacement for what is usually a Smalltalk VM. Right? So I only have one slide because well, the idea was to try to make a hands-on tutorial or something like that. Well, there wasn't enough time, but at least I'm going to make use of my time showing you code, right? So I'm only going to introduce the key aspects of the system with this slide, and then I am going to show browsers. Well, what we have here is a diagram of a typical Smalltalk VM or for any other object-oriented language. We have one layer, the one in green, that represents the objects of the language in the image, right? Like you have, I don't know, order collection, you have also meta-objects like the classes, the method dictionaries, and everything needed, or not everything, but most things needed for execution, and also for representing the knowledge in our system, right? But then you have in the gray layer that there are primitives and there are things that we cannot see, like lookup or the JIT compiler or the memory manager. They are there, but we can only access them through some strange or hacky ways of coding, like writing in a place primitive, or maybe we don't see it because the compiler generates something that we don't see. And our idea is to let anybody get access to those great objects, right? Make them actual Smalltalk objects. So we try to make this what is called the dynamic metacircular runtime, which basically reifies all the concepts that are implemented in a traditional VM. Well, I guess that's basically all I have to say about this. And so what I'm going to do is to load an instance of VDMR. We are going to basically, I don't know, travel around the system, and I have one idea, which is to implement something like something that you would normally implement on the VM layer, right? Like writing, for example, C code, or if you are a script VM developer, Slam, right? So I am going to try to implement a very simple version of read-only objects, right? This is like the typical research case. Like we want to have read-only objects in our system. So how can we implement that? Well, we could, for example, work at the image level and try to get access to all the rights of the object I want to make read-only, and then stop all those rights. There's also another possibility, which is to go to the VM call, download the code of the VM, change it, and then compile that VM, load the system, try to make it work, right? That's the traditional VM workflow. And what I'll try to show that is that it is possible to have a similar workflow to what we have in common systems that we program every day in Smalltalk. We don't have to do all this compilation, I don't know, traditional developed system for virtual machines. We can do something more dynamic, right? It's like well, there have been many talks here about how we can improve our system and how the IDE fails if we have to get out, right? So, okay, let's try to make the IDE not fail, success. So, well, here I have a transcript, and I have some ideas. I'm going to implement this read-only object in some place, I don't know where, maybe. Let's just open some project I have around, I don't know. I choose this one because, I don't know, I don't remember. But I'm going to implement this read-only object, right? And so, the first thing I'm going to do is to create a subclass of object that will be this read-only object. And it's going to have some state, for example, right? Like something that we want to make read-only. So, well, what would be the first thing to do? If I want to develop some new functionality, maybe I would like to, for example, make a test so that this functionality works, right? Well, so let's write some tests for this. Not only I'm going to make this read-only object, but I'm going to make, for example, a test case, and we are going to make this read-only test. Right? And the first test that I imagine I would write would be like test read-only, right? We are trying to test this. And so, what should this test do? I don't know. Just create an object, try to assign the state to the object and check that it's read-only. I don't know, this is the simplest idea I can get, right? So let's try to do that. Let's say, okay, here we have a read-only object, and let's say that we are going to try to assign the state and a test that it fails, right? So, for example, this is the idea I have in mind. Well, what should write? For example, I don't know, read-only error, right? We don't have this, we are going to implement it. So let's open another browser here in the same project. Let's go to read-only object and also implement an error, a kind of error, right? That just tells you that it's a read-only error. So the description is going to be I am a read-only object. Right? Yeah. If you see that I make any mistake, just correct me, because this is programming for everybody, so you are also programming here. And I could make mistakes very easily. So, well, okay, we have this description, right? We have this error object, we have this read-only error, and there's, I think, there's, okay, there are some temporary object yet. We have this code, right? Well, I didn't implement the state setter, right? So let's open a browser here. Okay, that's much clear. Well, so we have, I think, most of what we need for running the test. And it should fail. Well, and also I'm going to say I was very nervous about running all this because the system itself is very experimental. So it's not only that we are going to work with VM stuff that you can easily break, but also that the system can easily break. just by running some code that you didn't plan, but I guess everything will work. I expect that, but we may have some trouble here and there. So let's write an if else, right? Why? Because if you do this, for example, set the state, it just worked, right? I just set the state. Because I didn't do anything to make this object read-only. It's not that by calling it read-only, it's automatically read-only.
It's not that good.
Not that good. Sorry. So, what can we do? Okay, we have to make this object read-only, and how can we do that? Right? That's the question. We are Smalltalk programmers. We are. Yeah.
You throw an exception in the setter.
You could throw an exception in the setter. Yeah, well, that would be a bit tricky, right? Very simple. Well, but yes, the idea is that we should try to do this, writing some Smalltalk code, right? We don't want to go to the VM, like traditional. But we want to go to this runtime equivalent of the VM. So,
how do you assign variables? We have a method to assign variables.
Perfect. That was what I wanted to hear. So we have this method, right? It's assigning a state. So we can see that here there is a tab for the bytecodes of the method, right? And we can see that, well, this is a method that has 4 bytecodes or something like that. The first is to say that there is actually no frame for this method. And when we talk about there's no frame, it's like we are thinking a bit in assembly, right? Like the native code that is going to implement this method is going to have no native frame. Then we have here that there is some R thing that is going to be loaded with an argument that comes from the stack, right? And if you see the method, then you know that state has one argument, which is the object we are assigning. So what this says is that we are going to take that argument and put it on a register, which is called R. That means the receiver register. And then we are going to store into that same object, which is pointed by R, we are going to store we are going to store into the into self, right, which is in another register. We are going to store that value, which is stored in R. I'm going to repeat it because it was a bit messy. So we have the argument in the R register, and we have self in another register. So we are going to store R in the place of self that holds the state variable, the state instance variable.
The 6C file that loads on top of the stack picks the stack or pops the stack?
Neither.
Yeah.
Neither. Because the argument comes from the previous frame.
Okay.
So
it shouldn't modify it.
It shouldn't modify the stack. Right. And we can also see a bit more of detail of this, because we have here another tab, which is the disassembled code of that. Well, this is the kind of things that can fail.
Sorry.
So let's run it again.
Did you save your image?
We don't need it.
Yeah.
Let's check what we did. Because there were some patches that I had to load before doing everything. So as I didn't load them, I think it's like that. Wow. I guess we are in So here we have the disassembly for the bytecodes, right? We have here the bytecodes, and this is the disassembly of those bytecodes. And I mean the disassembly, actually this is the assembly, right? But each method in B has a corresponding native code, which initially usually is nil, but when you want to execute it, you're going to create this native code, and you're going to create basically some assembly for it. So we can go there, fetch that native code, and see what it contains, right? And here what we are seeing is, well, for example, the register that we mentioned before, there was, for example, some R register, right? And there was something that we call self. Well, here we don't have that because it's native code for the target platform, Intel 64-bit. So what we have here is RSI, RAX, and well, in the shape of our code is such that the R register is always mapped to RAX, and the self register is mapped always to RSI. So when we see here that we are moving, for example, RAX into RSI, we are saying, okay, somebody sent us a message, right? That message was being received by somebody that stored the receiver in RAX, and now that object is self, right? So to make it self, we are going to pass it to RSI, right? And well, then we see, for example, there is some movement in the stack. Here, the screen is a bit small, but we can see that there are numbers here, like 1, 2, 3, which map to bytecodes. So this corresponds to the second bytecode, which is, okay, take the argument from the stack and place it in R. And then finally, we see that we store that RAX, which is the argument, into someplace into the receiver. As this is an object with only one variable, one instance variable, then the receiver is being pointed directly to the first slot. Right? This is the contents of RSI. And well, finally we see that, for example, here there is a call which is a bit strange because we didn't make any message sent there, right? Why should be a call here? But the interesting thing here is that as this is very dynamic and reifies everything, or many more stuff than normally, we can go here. This is a compile method. We could, for example, see the native code. We are inspecting that native code. We can inspect the disassembly of the native code and see that it's the same than the other one. Well, maybe there's some different pointers could have changed or moved, but it's basically the same. And we could also, for example, say to the compile method, or to the compile method, just say it send sites. What are the send sites? This kind of native code is stored with references to objects, and the everything it references is stored in somewhere else. So we can ask the compile method what is it storing, right? It's not only the literals of the compile method, but also some things that are stored in the native code. For example, the send sites. And so here we can see that the object pointed, and this is tightly mapped to the code. Here, there is a pointer here. So what we see is what does that pointer mean? And it says, okay, you are invoking proto-object called refer is needed. No, well, I know the VM, I know what this means. Maybe some VM engineer also knows what it means. We are storing into an instance variable, right? And so if what we are storing is new and this self-object is old, then we have a generational garbage collector, right? So we have to remember that this object is old and it's pointing to a new object. So this call is actually an invoke into that code that does a check and saves the reference if it's needed. Well, so we can, yeah.
Sorry, a question that is more basic than what you are saying, but you have the pointer to the compile method that is being called as a integer, as a constant, that you call, right? That is a decimal number.
Yeah, something like that. Here,
yeah.
Give me this.
Exactly that. But what happens if you will compile the other method, the pointers are invalid?
If I recompile which method?
The method you are calling here.
Yeah. Well, it will generate a new sense type. It will generate, yes, a new pointer.
When you say the method, it checks all senders or data or something like that.
Well, actually what it does is to look into a map of all the implementers of the selectors. For each selector, it has to invalidate all the places if it's needed. Yeah. This is being done. But it's not a problem because it's not that frequent, right? It's not that you are changing all the code all the time. You are just changing some code sometimes.
Okay.
Questions up to here? Yeah.
What is your inspector? You showed both this assembly, 64 bits, as well as 32.
Yeah.
Lots of inspectors.
No.
Yeah, it's a typical inspector, right?
Open native code.
Native code,
Yeah,
it has aspects, and you can, because the native code has a pointer to the actual byte array that calls all the instructions. When you say, for example, move RSI REX, this is going to be encoded into Intel's own format for instructions, right? We are saving that into a byte array.
Yes.
So it's a plain object that you can expect, and it's here. This code references to the native code already encoded. And as we are here inspecting the native code has some aspects that you can browse or inspect, which is, okay, let me see this code as if it was disassembly for 64-bit Intel, or if it was 32, but if you see it as 32-bit assembly or disassembly is nonsense. Yeah.
Okay. I understand.
Short answer. The inspector is not smart enough. Yet.
Okay.
So it gives you both options.
Exactly. You need to know. Okay,
the
exactly.
right
Option. Okay.
Okay, so we'll try to keep going. There's not that much time left, and so how can we make a read-only object? That was the target, right? But it's very interesting because I'm showing you all the system, and it's all Smalltalk, and I don't know. For somebody who doesn't understand assembly, it will be harder. But the problem is that we are actually we are talking about the system implementation, right? So we have to talk to the assembler. We have to understand some assembly to do a virtual machine. If you don't understand that, it's going to be very hard. But we are trying to make it as easy as possible for you to understand that. That's the idea, to make it very simple as possible. So here we have this state, right? And we want to make that when somebody tries to sort to the state, we are going to stop it, right? So why don't we go to the JIT compiler and modify it? Because it's made of Smalltalk objects. We can change it on the fly, right? So, well, I know where that is. You don't, but if you get some experience with this, you will get. So we have this group of objects which are that are the nativizers for the bytecodes, and you can see that we have many of them. There's one for each bytecode in the system, right? There are many bytecodes. And if we go down, we are going to see that there is some store instance bytecode nativizer. So this is the object that is going to be used when we have to create the native code for that bytecode that we saw before that stored into store instance variable. And we can check the assembly. Well, this is not the last one, but forget about this part. We don't really care.
No.
Right? Actually, we're going to save, and we change the bytecode nativizer. And it's very strange because I just touched a piece of the Git compiler, and I don't know.
But
It's being used just now.
right now.
Yeah.
But
Well,
only when you store something in an instance variable.
no, but the thing is that it actually is not being used right now because it's going to be used when you have to create some native code.
Yeah.
So let's check what this does. Okay, it says save the context switch point. We do this for every bytecode, like we could switch into another thread and into another process or something like that. Okay, don't pay too much attention. Here it says it uses some self-register. Actually, this should be like this. It should have been like this forever. So we are going to change it, and we change it again, and it didn't crash. So, well, what it does, it says, okay, store what we have in the R register into the self-register at some index, which is the index that corresponds to the instance variable we are trying to store. The Smalltalk compiler created the bytecode to tell it, okay, we are going to store an instance variable, and the number is going to be this because we can see the meta class and check what is the index. So here we have the code that generates the native code. And actually we can see that afterwards it says whole reference is needed from self. It's what we saw with the send site, right? The right barrier. So let's, for example, add some code here. And okay, so we have to make this object read-only, right? How can we do that? Well, we are going to add something here to send the message when we are trying to do this, to store into a read-only object. So I'm going to start here with something like, okay, let's take the compile method we are trying to nativize. We are going to ask it for the class that is nativizing for. Right? And we could, for example, ask it if the class is read-only, then we are not letting it to be read-only, to be modified.
Do classes understand?
No, they don't. And if I accept this, everything will crash, right? So this is one of the disadvantages that we have up until now, that we are changing something that is being used at the same moment. So if we break it, everything will crash. So we are looking for mechanisms to be able to do this safer, in a more safe way. Okay, so we are asking the class if it's read-only, and if it is, we are going to say, okay, read-only error. And what is this emit send? It's a message implemented by the method nativizer that basically tells at some point to the assembler to generate the code that emits a send, a message send. So,
To whom? Which is the receiver?
That's another good question. To anybody who is being held in the R register.
Okay.
So, if we do this, we are going to send read-only error to any object, whatever it is in R. But we can see here that what we have in R is actually the object being not the one being assigned to, but the object being assigned. What we are passing as a parameter. We saw that. So we can say here, okay, we are not only going to do this, but we are also going to do this. Right? Because now we are going to put in our register what was self. And then we are going to send it the read-only error. Right? We have to make this class read-only, so we have to be careful here. And this is being sent to the class, right? And so what we are going to do, this is just a small demo, so just, let's say, self equals read-only object. If that happens, it's read-only, if not, it's not, right? We agree on that? Okay. And so... Sorry?
Read-only object is read-only.
Yeah. Okay, let's do this. True. Okay, perfect. And let's say false. Perfect. Okay, so let's go back here. We have this read-only message. We only miss this is read-only error, right?
Yeah.
We could implement it anywhere. It will get. If we don't, we just will get. Does not understand. Just we are going to say, let's implement it in object, just that we can get a nicer message, and maybe this crashed. No, because I didn't. Some errors.
The receiver would be true, right?
The receiver will be true of what?
Of this read-only error, because the receiver is the answer of the last send, which is true, or false.
Okay.
We can check later. So we have this implement. I don't know if it's still here because we crashed at some point, but read-only object, read-only error. Signal. So okay, it's there, still there, right? And it has its description. Yes. I am read-only. Wow. Perfect. So we have read-only error. We have. I believe we are not forgetting anything. I could be wrong.
Say the image before saying the
We never say the image. So there it is, right? And it still didn't crash. Cool. And we had a test because, well, that's the first thing we should do, right? Let's run it and cross our fingers again. It failed. Okay. Why did it fail?
Because you didn't recompile the state protocol.
Good. It's good. It's good to have smart people around. Okay. What's the problem here? We are sending state, right? And we already executed state. So we are going back to some other browser where we had the method there. I don't know if I still have it. Yeah, it's here. And if we go to the disassembly, right? Well, I don't know what happened here. Let's check. Inspect the method. Native code. I don't know. It has some native code, and well, the native code doesn't have another extra send. It's still the same amount of sends that it had in the first time. So the problem is that we changed the JIT compiler, but we didn't renativize this method. So let's invalidate the native code of that method. And we can see here that the native code should be new. Okay, now it's in. And so let's run the test again and cross our fingers again. It's still failing. Well, here I don't know what happened.
It's still new.
It's still new. We are probably inspecting another version of the method, maybe? I'm not sure.
Well, maybe there is a bug in the test and the test before it executes the stage.
Yeah, no problem.
Okay, so let's just do this. Well, and now it crashed. Well, that's the problem with demos, they can fail. But it shouldn't have, right? And it's a bit sad that it crashed. So, well, it doesn't really matter, because the idea is that we were able to implement all this and letting many of you that are not VM developers still with me, which is cool. So I think that this is a leap forward into being able to modify any part of the system. Because it's not only that you have to, I don't know, you are going to change something in the virtual machine, like the GC algorithm. You could improve anything. Like, when I was doing this, I discovered a few problems with the code and said, oh, we should implement this, which are the same sides of the compile method, and added some methods there, and found some problems on other places, and I improved. So, if your virtual machine is traditional, you are never going to take the work of going back to the C code and improve something. But here, you have all your code in a place where you already know, that you already know how to work with. You have to be careful, as you are careful when you are modifying meta classes, for example. So if you're going to add an instance variable to class, like I know somebody who's going to do that today, well, you have to be careful, because this is the description of how all the system works. So if you go wrong, you will crash everything. So this is the same here. But we are, I don't know, we are trying to bridge the gap between who is a VM developer and who is a typical Smalltalk programmer. And you can also understand many of the concepts. Like, it's much easier for me. I guess that for people that are not VM engineering, it's much more easy to understand the concepts if they are, if you can expect them, if you can debug them. So, well, that's my talk. Thank you.